There you go. All right. Well, it's my pleasure to introduce Dr. Alexander Murphy. He is actually an alumnus of our mechanical engineering department here as an undergraduate, and then he went on to Georgia Tech to get his master's and PhD, and is now a postdoctoral fellow at the University of Texas at Dallas. So he's going to tell us about some of his experiences there, especially about his research on engineering design and education. And before I turn it over to him, I'm just happy to see so many of our graduate students here, and I think we can learn something from a recent PhD about his postdoctoral experience as well, as he moves toward the job search. So, anyway, Dr. Murphy,
thank you.
For being here.
How many are you all in the mechanical department? Everyone? No? What department are you from? Chemical? Cool. Well, I'm glad you're here. And how many of you are grad students, out of curiosity? Wow. Okay. Yeah, so I'm Alexander Murphy. You can call me Alex. I go by Alex. I'm going to talk about my research specifically. I like to introduce the research area because it's not necessarily common at all programs, and it's something that's sort of up and coming in United States programs, kind of in general. Maybe over the last 20 years, programs are starting to pick up on it. As you said, I graduated from here in December of 2016 in the mechanical engineering department. I also was in the Honors College and had a great experience over there. And I got a minor in creative writing, which was great. Yeah, and then I went to Georgia Tech for 4 years. I got my master's and PhD in mechanical engineering up there. These dates are really close together. I get asked about this sometimes because Georgia Tech you don't have to have the master's first. You just kind of pick it up along the way. So I applied for it, at the end of the spring and got it. And then now I'm a research fellow at the University of Texas at Dallas, working with Dr. Josh Summers on the same research area. It's been great. I've been there about a year. All right, just a really quick overview of what we're going to talk about. So again, like I said, background of the research area, talk about my past work. Past work is largely dissertation. My current research, this is exclusively what I'm doing at UTD. And then just a little taste of like future directions that I think I might be going. And hopefully we have a decent amount of time for questions at the end. Background. So we're going to talk about what is the design process in case no one's explained this to you or you haven't been exposed to it. And then what is design theory research within this area of study? And then again, kind of distilling even further what approaches I take and what I specifically do within the research area. So this is one potential depiction of the design process. There are many. If you Google it, you will find hundreds. They're all specific to fields though. So this one's tailored a little more for mechanical engineering, but you're going to start with product definition or problem definition. Sometimes replaces that one on the far left. And then you go to concept generation. This is going to be stuff like idea generation, just brainstorming, things like this. Concept selection. So once you have a bunch of ideas, how do you go through and select them? And then embodiment design and detail design sometimes get mixed up. It's kind of confusing to separate the two of them because sometimes the methods overlap. But embodiment design is really taking a concept and making it what I'm going to say real. So this could be taking a bunch of sketches or even really, really ups and putting them into CAD, right? This could also be putting them into a simulation depending on the type of work. It also could be moving from drawings of a website to putting it into code that's eventually going to be the code that runs your GUI or your website or whatever it is. And then detail design is phase of trying to substantiate your concepts to getting it ready for manufacturing and distribution. So this is things like tolerancing, dimensioning, clear dimensioning, creating drawing files if you're mechanical, right? Or doing product. That's the general idea. You can also distill it down to like 3 steps. Kind of develop, refine, and implement. Where develop is this brainstorming, idea generation. Refine is this prototyping, iteration thing that you hear about. And implement is sort of logistics, design specifications, and product service launch. How are you going to do the life of the product or the service or the system? I always want students and engineers or whoever it is that is doing design to spend more time in that direction, right? I think a lot of times that there's a lot of information to just go ahead and prototype early and all this, but I don't think sometimes I see a lot of, even in industry, people start prototyping and coming up with ideas before they even understand the problem. Or even if the problem should be solved is kind of a spicy take on that one. Sometimes it's better not to solve it. Anyway. I'm not going to spend a ton of time here. These are just some cliche depictions of the design process. I say cliche kind of lightly, but this is the double diamond that was sort of originally developed by a company called IDEO. IDEO designed the IKEA carts that like can roll around in all directions, you know, it's like this revolution of shopping carts. But the idea is that you have divergence and convergence, right? So in the early stage design, when you're exploring, you want to go broadly, then you want to narrow it down. This would be something like concept selection. And then once you have a concept, again, you're going to diverge again and explore a bunch of ways to solve different issues with the design, et cetera, and then converge on the final solution. I think this is a little unrealistic. It's good to talk about conceptually. I think this is a lot more realistic. Again, I know it looks silly and simple. This is kind of the fuzzy front end. You see this a lot in UX UI courses, like early on. But it's this idea that there's a ton of uncertainty in the beginning of the design process that you slowly distill down. I like to think of all these squiggles as little diamonds, right? If you were to have sometimes 100 of them, if you look at product development in industry. Right, but you know, early in, you're doing a lot of research and search and benchmarking and stakeholder analysis and all this stuff. And then you sort of prototype in the center until you end up converging on a final solution, right? This is some work I did now. This is just to show just a piece of the breadth of topics that we cover in design theory. This is a literature, well, it's like half a literature review, half a meta-analysis. But basically, we looked at a whole bunch of topics related to prototyping in the orange and the teal in the bottom and the left. And then on the purple is all this design cognition topics that at the time our research lab had studied previously at Georgia Tech. Some of these terms are a little weird, like what is quick modeling? Don't worry about it. It's like defined in the paper where this is, but the point of this is to show you that there are a ton of topics and that not everything is like evenly covered, and there's even some gaps in the literature, right? And so that's what we're trying to do in our field is find these gaps, put things together, talk about collaboration and teamwork, and overall improve design outcome during the design process. And I just really like this graphic. Okay, so what do I specifically do? That's unfortunate, isn't it? What I specifically do is design cognition and engineering education research within this area. So almost all of my work involves human subject studies. So if you have any experience dealing with the IRB or the Institutional Review Board, you know, I have to get approval to do all the research that I do. Very often it involves students. Sometimes it involves industry if you can get a hold of them, but they're a little harder to track down. I use both quantitative and qualitative methods to do this. So quantitative being statistics or design competitions or some other scoring method that you might find. A lot of the quantitative methods that we use or I use come from cognitive psychology. And then qualitative methods. So this is like semi-structured interviews, fully structured interviews, phenomenologically structured or phenomenologically based interviews. This is also content analysis and thematic analysis of like transcripts from text or interviews. So something that is departments are sometimes interested in is like at the end of capstone, taking their final project reports and analyzing what they learned, what they did, what's in the reports. Is there any consensus across students or something like this? That's sort of the qualitative methods approach. The far end of the spectrum would be ethnography. So this is observing people in a space and trying to understand culture. We did this, I didn't do it personally, but my research group did a project on this at Georgia Tech, trying to understand women's experience in the makerspace. Again, this isn't my work, but that's the type of thing you would apply that to try to improve the space or the culture of the space, et cetera. I put this up here because some people have never done human subjects. We're always very sensitive to participant student experience. So a lot of times we'll go into a classroom to collect data, but we want it to fit curriculum. So we're not gonna go in there and do something completely random. We want it to be timed properly throughout the semester so that it's like at least partially relevant to what's being taught. If I can analyze data fast enough, I always go back to the class at the end of the semester and show them their own results, obviously anonymously. But yeah, this is the kind of stuff I do to study all of the topics that I'm interested in. So what have I actually done? This again is going to be my dissertation. Pretty cleanly cuts into two halves. It's a long story why that happened, but I would say a solid half of it is on systems thinking. This is going to be an intersection of, which I'll explain what these are, but functional modeling, systems thinking, and design representation. And then the second half is on prototyping, and specifically I looked at differences between iterative and parallel prototyping approaches. I love this quote. we're going to talk about mental models a lot. But mental models of physical systems are internal representations of external systems. This is a quote by Mark, a book, Knowledge Representation, and it kind of is a synthesis of all of my body of work from my dissertation, I think. And it's really important, a couple words to point out is physical systems. So people have done research on parallel prototyping, for example, and programming, because it's a lot easier to do. Doing it physically takes a lot of time because you have to produce the physical thing. And then this internal representations, these are your thoughts in your head, how you think the world works or how you think something works. And external systems is this sort of your internal, what's in the mind of how you think a system works and the system exists in the, quote, real world, right? So if I asked all of you how a bicycle works and to explain it, you all would give me a slightly different answer, right? Not that any of them would be right or wrong necessarily. I hope if you're an engineering and a graduate student, you have a general idea of how a bicycle works. But Lawson proved that this kind of isn't true. I think there's going to be text that's here, yeah. So this was research done in 2006 that informed a lot of my dissertation work. There's also, if you've ever seen this sort of thing, Discovery Channel picked up on this and did a couple of like episodes on one of their, I don't remember what it was, but they actually like really quickly built people's bicycles. And of course they don't work, right, in a time. But yeah, you know, Lawson had participants which were expert cyclists and then just people who owned bicycles. Put the frame, the pedals, and the chain on this blank bike. And then down here, she also had, what would you call, variations. So this was a frame example, and the participants had to select the right ones. Yeah, overall, participants greatly overestimated their ability to do this. And the cyclists did perform better. There's also gender differences, which was surprising and brave to publish. The point of this is that this is the sort of mental model research that's done in psychology, and this informed how I did it in my work. The other piece I think that you need to kind of understand for this to make sense is functional modeling, functional decomposition. This is a strategy that we use in design theory and design education to break down a problem. So you've heard that kind of the cliche of form versus function, I'm sure, at some point or another. This is purely function. So we're trying to get rid of any, we're trying to represent the problem in solution neutral terms, right? So essentially the primary function of a can opener is to open cans. We have energies in thin arrows, materials in thick arrows, signals in dashed arrows that come in and out of the system. System boundary, you can think of really similar to thermo, right? You define the system boundary and what passes through the system boundary. And then down here is the actual functional model. And these can be more detailed, less detailed. It depends on what you want to use it for. But essentially, you know, we're talking about importing human energy. So this would be, like, you can imagine it being the hand, convert human energy to mechanical energy. So this is what the function of the hinge is doing, right? And et cetera. And you can follow it through. There's been a ton of work on this. It is even a little niche in my field, but the people who like this research like really like it. And I happen to be one of those people, unfortunately or fortunately, depending on how you look at it. Anyway, there was a industry interest in this, especially for innovation, because if you could represent products in this way, you might be able to systematically or computationally find products that are related just by the function chains themselves, to do like analogical design, right? Or to find inspiration for design, et cetera. I didn't do any of that per se, but just to show you one way that this might be valuable in design. So the idea was we wanted to see what the impact of teaching students was, or teaching students functional modeling was. And so we collected mental models, similar to how Lawson did of some simple products, taught them functional modeling over 3 weeks, and then collected their mental models again. There was a control condition, which I'll show you results from, that did not do functional modeling. And in those 3 weeks, the research team that I was working with really carefully selected topics that we didn't think was going to interact with mental models, and we don't see it interacting. This is collaborative, different pieces of it. I was at Georgia Tech, so obviously Georgia Tech. Hope College is a liberal arts university in Michigan. And then James Madison University is in Virginia, and they have a Bachelor's of Science in Engineering that's ABET accredited, so it's interesting. That's not discipline specific. So we had 3 very different universities, which was kind of the goal. And this is what ends up happening. So we asked them to fill in outlines of hair dryers. This is the same student before and after. You can tell this is the same student. Let's see if I can do this. No, I can't. You see how they drew the fan on the left and the fan on the right? It's kind of similar, so to kind of prove it. But the things to notice here are before and after is after learning functional modeling, the student has decided to indicate a motor, and they've also really connected everything, right? Let me see what else. They've also, and I think they just forgot on the left one to be fair, but on the right one, they indicated error on both sides instead of just one side. This is really indicative of what we see across the data set. This isn't just a one-off. And what we're not claiming, or I'm not claiming that I've magically made them understand hair dryers better. I think it's giving them a framework to communicate their knowledge, right? One of the other things, it's not the case in this example, but what we see a lot of the times in the data is before learning functional modeling, they won't put a motor and then they do. Well, I guess this is represented here, but if you go up, you ask the students afterwards, like, hey, why did you not put a motor? They're like, oh, I just didn't think to include it. I know there's a motor, right? And so I think the learning functions is teaching them that, like, hey, this is a discrete step in this system that needs to be represented and communicated, right? So how we score this and how we get data out of this is the rubric. I don't expect you to read this, but there's a bunch of questions that we've used and validated a bunch of times. The blue ones are high-level systems thinking, or what we've deemed high-level systems thinking. Orange or red or whatever it looks like to you is components. So those are a little more self-explanatory. And then the last ones are like what we've called low-level systems thinking. And this is what we end up with when we score this. So these are graduate engineering students. On the left, there is no change. The error bars are like very overlapping, which is a kind of a rule of thumb to say that there's not significance. It's not always true, but it is in this case. And on the right, you see improvement, right? This is really cool to see. It means that what we did teach in those 3 weeks didn't impact anything, which is good. And then function does have an impact. And again, remember, these are graduate students. These are not undergrads or anything. So this is not only a case for teaching function, but also I believe that has implications for thinking about how we represent systems and sort of like if you were an industry job and you worked at a nuclear power plant, I wouldn't be surprised if you know, doing something like teaching industry professionals function will have them communicate better their knowledge about the system, right? Which could have implications for troubleshooting and all sorts of. I think I have another one here. Yeah, this is just the stats. I'm not going to spend time here, but the bottom three are significant if you take it at 90%. Here we think it's a ceiling effect that it's not 0.05, but we presented it at 90% and no one argued in the journal. So yeah, those are very obviously significant. This is engineering versus non-engineering students. Engineers are on the left, non-engineering students are on the right. Not only do they both improve, but the non-engineering students, for whatever reason, outperform the engineering students. This is really funny. There's a couple of reasons why this might happen. It could be motivation from the engineering students. It could have been the instruction, right? Different instructors taught function. But in any event, the fact that this is even possible is pretty fascinating, at least to us. This is currently under review too for publication. And then this is a hard transition straight to prototyping. So sorry about that. But we're going to talk about the second half of my dissertation, if you remember, was on prototyping and not this mental model system stuff. Okay, so basically, I set up a design competition with undergraduate students, and we had them 3D print little catapults in a design competition. It took about 8 weeks. We split them into 2 groups, a parallel condition and an iterative condition. The parallel produced 2 prototypes and then a final prototype, and the iterative did 1, 2, and 3. The thing to note here is that we controlled the learning loop. So if you think about what prototyping is, it's an opportunity to learn from your design and your design concepts, right? What we did is we did not return their prototypes until we had both. So they could not learn from their concepts. They learned from their concepts at the same time or very close to the same time. So, you know, in reality, time goes one direction. True parallel design is only maybe possible with multiple people or an AI or digital twin or something like this. But in this case, we controlled the learning aspect, which we think is the point of prototyping anyway, where in this case, they didn't. The other thing that gets pointed out sometimes is that isn't there one round of iteration in the parallel group? Yeah, there is. It's literally impossible to design a study that doesn't have that, and it's really impossible to find a design scenario where that's not the case. So that's kind of my way out of that one. this is sort of the setup of the competition, and I won't lie to you, it's a lot like beer pong, foam balls, catapult, into cups. And then there was a whole scoring method based on how close they were to the center of the target and how close they were to the requirements, so the distance from the thing. I will tell you, it's kind of funny. The students are really bad at hitting the target, but we looked at other stuff too. This is kind of a real high-level summary of the results from this study. But basically, we think that the parallel condition here in gold is exploring more of the solution space. What we notice is that if you look at all three of their models, they're much more different than the iterative group. They also, if you do a chi-squared, not on competition score, unfortunately, because they were so bad at getting the balls in the cups, but if you do a chi-squared analysis on whether or not they scored points at all, it's significant that if you were in the parallel condition, you were more likely to score points or have success in the competition. And then I think the number one is a little strange, but basically students in this condition, I think a little bit because they perform better in the competition, had higher self-efficacy or engineering self-efficacy. And the last little piece is, this was very surprising to us because we would have thought maybe the parallel group felt pressured to produce more because they had to do two models that they felt like, oh, we didn't have enough time or we had more work. They didn't report this. So like there was a survey we did at the end of all this that they reported equivalent time, equivalent availability of resources. Do I have this here? Yeah, and then we did a qualitative analysis of their design reports for the project. This is one of the ways that we looked at it, how satisfied they were with their prototyping approach and whether or not they scored points in the competition, right? So you've got the two groups up top, whether or not they scored points, and then on the left, you have whether their satisfaction, their self-reported satisfaction. I'm gonna piece apart maybe one thing here because this chart is a little bit hard to dissect. And you look at this tall blue bar of satisfied students in the iterative condition that did not score any points. And then if you look at how many of those students in the parallel condition that scored points were not satisfied. You kind of see what I'm saying? There's like 3 or 4 ways to look at this chart, but essentially I will Spark Notes it for you. It basically says 3 different ways that no matter what, students wanted to be in the iterative condition. And I think this is sort of ingrained in us from school, that they're more comfortable iterating one at a time. They like incremental change, even though all of our data said that the parallel was better, right? And I think I have one more. Yeah, I have basically what I just said. The coolest result, I'm not going to read this to you, but the coolest result from this study, like the most surprising at the very end of it, was I just kind of ran a quick analysis and realized that 30 out of the 45 students stated that in the future, they would use a combination of parallel and iterative. And we didn't teach them this, we didn't tell them this. It was really, really cool to see that they learned that, hey, doing both of these is probably the right idea, even though they all wanted to do iterative more. It means that they learned something from this assignment, which goes back way to the beginning of when I was talking about being sensitive to curricular content and trying to teach them something through the research too. Right, okay, where am I at? Oh, we're good. So I'm gonna move on to my current research now. You know what, let me pause. I've been running my mouth. Do you have any questions about the other two? Maybe I'll take like 1 or 2 questions. Yeah. So the way, that's a good question. The way we did it, only if it went in the cups. Some of them did bounce off, but we gave them 5 shots and we took their 3 best scores. And over half of the students didn't even hit the thing. They were surprisingly bad at this task, which surprised us. So one of the things I eventually want to do when I have other more pressing things right now, but I want to do it with like either seniors or graduate students and see if they do better. These were first semester students. Yeah. And we also thought that at the time, like we thought about that, and the balls were real bouncy, to be honest. But they could have practiced. We gave them the cups and those balls we were going to use and the rubber bands that they needed. So we were hoping that they would, practice and figure it out, but they did not. Yeah, it's a good question. Any others? Yeah. I thought that the parallel, well, first of all, the hypotheses were based on, I thought they were going to score points, to be fair. But I thought the parallel condition was going to have an average higher score. And this is because I thought that they were going to, it goes back to, oops, this idea. I had this idea kind of in my head that they were going to explore more space. I'll tell you something that I didn't expect was that they very often completely abandon one of their ideas. And there's really no artifact of the other idea in the final solution. I currently have an undergraduate student who's analyzed the last is where we have the CAD files. So we're analyzing the CAD files to look at the, the feature trees in SolidWorks. And we're looking at like discrete functionality or how much of SolidWorks do they use, et cetera. And like so far, preliminary results kind of show that the parallel condition used a broader range of. Yeah, we're still working on it. That last half was not answering your question at all. Sorry about that, but yeah. Yeah. I think that students who were put in the, well, and ideally we would have run this study without them knowing about each other, but because of curricular constraints, we couldn't. It turned out that that was a positive, which is that that they sort of realized doing a combination was, but yeah, I think the students who were put in the iterative group were like, yes, you know what I mean? But I did go back to the class. This is one of those times I went back and showed them the results, and they were pretty surprised. I didn't show you a chart of the self-efficacy. That was a pretty stark difference too, that the parallel condition had higher confidence and lower anxiety. And that's one of the things that we're currently looking at is it because they explored more of the software? I don't think it's necessarily the prototyping approach that magically changed their brain chemistry, right? So yeah, last one, and then we can go on. Or look, you have a question? He asked one. Your turn. So are you asking if there's differences between students in different disciplines? Yeah. I have no idea. I would venture 100% of these students were in mechanical. Trying to find a course, because this took 8 weeks, and the professor who let me do this was she was like, yeah, go ahead. We'll just change the project to you. And I was like, this is awesome. Finding a professor that's willing to like let you come in and mess up their class this much is difficult. So I'm hoping that like if I'm teaching a freshman level class, then I can do it in my course, so it's less disruptive that way. But I don't know. I mean, it'd be interesting to do it in like civil, but I don't know how early civils learn CAD. I don't know. There's all sorts of, yeah. One of the things I do eventually want to start doing is replicating research with industrial design students. Georgia Tech has a big ID program, and they do a lot of what they're already doing in class. If I just collected it, I would have data, but it's a whole thing. So, okay, let's look at what I'm currently working on. Oops. So we have 2 topics, representation modality. There's 2 conference papers, and we're currently working on a journal article about to submit it, and then product teardown, which this will look very familiar when we get there. Okay, so this looks like a functional model again. This is a more traditional functional model. This is of a product. I'm going to ask you in a second what you think the product is, so see if you can figure it out. This is one representation of it. It's got kind of a left to right structure. Excuse me. And yeah, we've deemed this representation of this product a function structure that's traditionally found in like design theory textbooks. Then we rearrange them to align with the components in the product, so we call this the function graph. All of the elements are identical from the one you just saw. We just moved them, right? And then the last one is going to be the component graph. So in the same locations, but with a generic representation of the component that would be there, right? What's the product? You guys know? It's a hair dryer. You guys are way faster than the last time I presented this. Yeah, hair dryer, right? I also kind of primed you, but right. And so when you look at all three of these, the idea here is that there's variations in vocabulary. So vocabulary being, if you look at the motor at G here, I don't know if you can read it anymore, but it says convert electrical energy to mechanical energy. So that vocabulary is different. So for the left and the middle, the vocabulary is the same. The middle to the right, it's different. Right to left, it's different. And then layout, obviously, right? So the two on the right are spatially laid out identically, even though the vocabulary is different. And the two on the left are both function structures. If I gave this to anyone in my field, they would say, oh, yeah, this is a functional model. But the orientation is significantly different, right? And with the hairdryer specifically, it's very right to left, which wasn't necessarily intended. And the other ones, this isn't the only one we tested. There's two other products. I'm just showing you the hairdryer. That wasn't the case in the other ones, right? So there wasn't this sort of right, left, right bias, just for the hairdryer. And then we tell students to group the stuff. So we're looking at subsystem clustering. So this was really focused on the subsystem thinking part of systems thinking. I'm not going to read you the prompt, but this is what was given to students. They were told to pretend that they were managers of a design team, and they had to divide up their team to troubleshoot the product. And we gave them this extremely abstract depiction of what I just showed you, and told them they could group it in any number of ways. So we gave them enough options that they didn't feel constrained to these ways. This one has a kind of a horizontal alignment. This has more of a vertical. This is like I've circled everything, and this is I've circled almost everything in one circle. Right, that was kind of confusing, but something to note here is we did not allow students to put an element in multiple groups. There's an argument to be made that we could do that as well. We did it, this is the first time we've done it, and we wanted to force decisions. Second, completely honestly, it makes data analysis significantly easier. But it's something we're considering is overlapping. But we want to do this again in a different way before we do that, but it doesn't matter. I'm being confusing now. Okay, we put all of this data when we analyze their circlings into a bunch of matrices. It actually ends up being rather complex to analyze because you have groupings of 2, groupings of 3, and how to compare like an average group. Like if you take the whole, what is the most likely grouping? It's not that easy of a question to answer. Anyway, the way we did it initially is by calculating a similarity score based on pairwise groupings. So how likely is A to be paired with B? How likely is B to be paired with C, et cetera, right? And again, I don't expect you to read all this, but there were thresholds used. So 0.11 and 0.14 were used. Let me read. Yeah, this was to control just like kind of wild answers that were outliers. So we checked a few different thresholds. And then I keep saying we because it's me and the postdoc I work with. And to eliminate outliers from the data set, and we eventually end up with a value that doesn't have any physical meaning. Is that green clear to you guys? Oh yeah, it's not clear to me over here. It doesn't have any physical meaning, but it is how variant the models are essentially. And what we see is for the component graph and the function structure. So the function structure is the left to right functional model, and the component graph is the components. 5 out of the 6 cases at 2 different universities, we see that this is the most different. This is what we would expect. We also think that this one kind of anomaly in the top left with more data would probably be the other way. The mixer had all kinds of kind of quirks in it. But yeah, we're actually, on Friday, this data was collected again at the University of Rostock. So this caught the attention of someone at a conference, and they want to know how German students compare. This is a really, really cool opportunity because so much research in psych and in design and basically everything comes from undergraduate United States students, right? There's not enough research from other countries, and this is a cool chance to compare. And again, you wouldn't know this, but Germany specifically has a rich tradition in design. Like a lot of the seminal design textbooks come from Germany. So yeah. I think I have one more. Right. So we're also, I'm not gonna go into all of it. This is the last thing I'm gonna show you on this, I believe. But we looked at connectivity distance. So this is how many steps you had to go from element to element, and what was the likelihood of those being paired, right? So on the bottom we have connectivity distance. So this would be, at 1, it's 1 step away. whereas 6 is 6 steps away. And this is just what you would expect. There's nothing significant or profound here, but we would expect that the further connective distance that you would get lower pair occurrence. We are also, which I'm not showing you in this presentation, but we also considered spatial distance, like ruler on the page. And we're combining both those analyses to figure out what dominates it, right? Is it connectivity, or is it space on the page, or is it representation modality? And that's the journal article I'm working on. And then again, hard transition, sorry about that. But we're gonna talk about product teardown now. So this is the second thing I'm currently working on. This looks identical, this should look very familiar. We do mental models, but instead of functional modeling, we're doing a product teardown activity with undergraduate students. Product teardowns have a lot of similarities with like exploded views of products, which most engineers learn about. The idea of an exploded view is to see every component, and teardown is to sort of investigate every component, sort of through the lens of curiosity, right? This work, we collect, well, let me say this. So we give the hair dryers come back. Hair dryers are great for this type of research. It's a long story and it's kind of funny, but we give them hair dryers, tools, they take it apart. There's a guided task. It takes about 45 minutes for students to figure it out. The unfortunate thing is to run this again, we now have 40 hair dryers that we have to put back together if they didn't break them. But anyway, this is currently, like, we're analyzing this right now. We collected this like 4 weeks ago. I have an undergraduate student working on this. She's pretty excited. She helped design it. And this is funded by ASEE, which is neat. The idea for this came from the dissertation work, where part of the mental model task, we asked them, have you ever taken this product apart? And we didn't have the sample size or the effect size to say anything conclusive, but there was a huge difference between the like 6 students who said they'd taken it apart before, scored like astronomically higher than the other students. And so we were like, well, let's just literally do it, right? So that's what we're trying to figure out with this work. Yeah, that's her name. And then future directions, right? Yeah, I want to leave time for questions. So I believe, yeah, I'm only going to really talk about this prototyping stuff, but I'm also looking at abstraction in systems thinking. This is the kind of why are they not putting motors question. And the other piece of this is on that same task, we do a clothes dryer as well. One of the more shocking results that isn't exactly publishable the way the data comes out, it's not significant, but just I've scored hundreds of these things at this point, unfortunately. And the number one component that students, graduate students, undergrad students, and non-engineering students leave off of the hairdryer is the lint collector. This is shocking for 2 reasons. It's the only component that you literally interact with, and they're not putting it on the thing. And the second is it's like dangerous not to indicate it, right? I mean, house fires start from lint. It's a little dramatic maybe, but when you think about like a nuclear power plant, it's not that trivial anymore, right? I mean, why are they not including this thing? And I don't have the answer. I don't know why. I think one of them might be as you increase complexity, you insert more abstraction for cognitive efficiency, like communication efficiency. That's not necessarily a good thing in engineering, but I have sort of plans to figure this out in the future. Prototyping I'll talk about in a second, and then design with emotional intelligence. This is a far-reaching. I put it up here because it's kind of grab bag variety. I did a little bit of work on designer mood and creativity, and it aligns with psych research that shows that anger, an angry designer is more creative, and it aligns with research from psychology that says that an angry designer is less creative. They don't agree. And so we're trying to figure out, or in that paper, we tried to figure out what that looked like. But I'm also trying to combine it with this idea of empathic design, which is that right? Yeah, empathic design, which is this paradigm in design that sort of compels the designer to put themselves literally in the place of the user to better design for that user. It's related to universal design, if you've ever heard this, which is designing for everyone, for all users, and considering how you can create a design. A really good example of this is, do you know the most famous example? You know the vegetable peeler by OXO? Yeah, I see a couple people shaking their heads. It's like the most universal vegetable peeler. It revolutionized everything when it first came out, which sounds like a crazy thing to say, but the handle is big and has those rubber fins, right? They did this so that people with motor issues, people with disabilities, older people, and everyone else who is more normative can use this product. and it doesn't impact the people who normally are using it. It just makes it usable by everyone, which is the universal design idea. So trying to combine those topics is a far-reaching 5 years out goal. Okay, prototyping. If prototyping classifications and frameworks are new to you, this is just really quick. So people have talked about, this is in one of the textbooks that we referenced, but focused versus comprehensive. So focus is going to look at one feature of a design. Comprehensive is going to be the entire design. High fidelity, low fidelity. Low fidelity is cardboard duct tape. High fidelity is the materials you would use in the final product. And you can see there's a couple of different types of prototypes one might design. So like appearance models, aesthetic models, they would do this a lot in industrial design, are going to be high fidelity and a little slightly sometimes more focused. Demonstration prototypes, so this would be for stakeholders or investors. You want high fidelity and comprehensive, right? You pretty much want the product. Proof of concept is going to be kind of middle of the road. Fidelity and appearances aren't that important, but you get the idea, right? There's different things. Funny to point out, I don't know why that's out of the box, but typically not feasible is having a really low fidelity and a high comprehensive model. I don't think cardboard's going to perform the same as, right? But that's not why you're using cardboard. Anyway, this is just one. There's tons of these, which is part of my problem and part of my point. There's a ton of dichotomies in the prototyping research. So some of it is high fidelity, low fidelity, internal versus external. Internal versus external. Internal is like internal to the design team. So the design team's trying to learn something. External is like sharing information with stakeholders. Fully functional, partially functional. This is equivalent to focused comprehensive. Fully functional meaning it works. Everything works. Partially functional is I want to figure out how this one motor is going to move this one arm. Iterative parallel, I talked about that extensively, and then cost and time is maybe the most obvious dichotomy. There's nowhere in the literature that I know of, and I know a decent amount of it, and again, maybe fortunately, unfortunately, where this is all in one place. First of all, and there's, people teach versions of this, people emphasize different parts of this. What I want to do is look at all of it and create a taxonomy and kind of archive all of these different views and angles on prototyping. I want to look at how industry is doing it. There's a couple of papers that are already out where they looked at the entire product development cycle of a company's or from industry. And so doing 1, 2 more of these, looking at old work and collaborating with the people who've already done it, and then creating a framework that the idea is basically when should you create a high fidelity, external, fully functional, blah, blah, blah prototype, right? Like actually provide a guide to designers, engineers, students that is like, hey, this is the most appropriate type of prototype for this scenario, right? Which isn't just, again, when you look at all of it, this seems like it's good enough, but it's missing. Prototyping, should we do iterative? It's missing a bunch of this. And then validating this through experimental studies, which is what I always do. Possible funding, I've thought about submitting something like this to NSF EDSE. They fund things like this in my area, and then NSF, RFE, Research Information of Engineers, because with step 4, we would be sort of doing this with students, and there could be the education component is why it fits into here. But yeah, this is just a taste. I'll leave this up here. Let me see. Yeah, we have acknowledgements and then just articles. We don't need to look at that. We can leave it here. So some of this stuff is like led into each other, right? Admittedly, this one is maybe more in the blue. Is it blue to y'all? Yeah, blue track, but I stuck it down in the bottom. So yeah, thanks for listening to me talk, and I'm glad to be here. It's exciting to talk to USF students, and I'm happy to talk about it. So, yeah. Okay. Yeah.
And then you were scoring them based on their kind of like rough drawings of your dryer at the beginning and different.
That's part of what we're scoring, yeah. No. Oh, on the drawings? Yeah, absolutely. Yeah. So one of the things we're looking at is knowledge transfer, or sometimes it's like mislabeled as analogical reasoning, but it's not really analogical reasoning, but it's this knowledge transfer between systems. That's 100%. So we didn't just ask them to do mental models of a hairdryer. We also did a clothes dryer and a vacuum cleaner. Funny side note, when we first started this research, we were also doing leaf blowers. That was a disaster because we would get electric ones, gasoline ones, nuclear powered ones. I mean, it was just, so we dropped that one. There was a lot of inconsistency. It's the same problem with like a grill. You know, some people have a gas grill, some people have a char fire grill, some people have a Traeger, right? So, but yeah, that's something we're looking at for sure, is the knowledge transfer thing. What else? Go for it. This? Well, this is a good question. This was printed on the packet, on the task packet, and the C would have been representative of one of these elements. And so we were showing them that you could group them together any way you wanted, and we were trying to encourage them to truly do it. We didn't want them to be biased and think that they had to do small groups or big groups or whatever. So that's all this is. Yeah.
So if you look back from history, you have different classes of engineers. For example, people made the rocket and the moon, and the designers in World War II. Obviously, they had much higher motivations than say product designers do today. Do you think that when you're looking at emotional intelligence, that has a lot to do with it, the raw motivation versus, say, whatever emotions they might be feeling at the time?
Yeah, I don't know. I mean, I think a lot of times we narrow the scope to look a lot more like what industrial design does because it's more easily collected and things like this. I have, asking about like how the design process changes in terms of like strong sweeping senses of like national pride is a very different. I think you would need sociologists, anthropologists, and all sorts of. I mean, I don't know. Maybe I think the mood is more immediate than something like that. So we're talking about like you're having a good day, or you had a bunch of caffeine, which I don't intend to do this, but let's say this. I really shouldn't even say it, but like if I gave every student 3 shots of espresso and I was like, okay, we're going to design something, it's sort of that more immediate. And it's more just trying to apply what they've looked at. And I think I said this wrong when I was presenting. I said that psychology has shown that their anger is better design. I didn't mean that. They're higher creativity. So anger is either associated or not associated with creativity. And there's a third piece that I usually save for if someone asks me a question about it, that probably the literature that I believe the most that's come out of this in psychology is that anger is very good for amount of time, and then it drops off significantly, right? Like lower than steady state. So like that initial being upset and motivated is very good, but your body can't physiologically sustain that. Yeah, it plummets. Yeah. Yeah.
And this may be just a stereotype, but I don't know if you think of creative people in the arts.
Uh-huh.
I mean stereotype, but unless you view it as people need angst or anger to write better music or paint better in some cases. And some people relate that sort of archetype person to a left brain versus a right brain engineer person, right? Mm-hmm. That doesn't hold true for everyone. But I was just wondering if you could just comment on if that parallels what you see with engineers and design or not.
So what we did was measure the current state of our participants. We're not trying to make our participants angry, but I think the comment about art is interesting because I do think if you ask professional artists about their most creative moments, it's either times of like high positive or negative emotion, or they're doing something that I'm not going to say publicly right now, right? But a lot of times if you ask them, the process starts that way to kind of open up the possibilities in what I call the solution space and what I do, but sort of the creative space. And then they go to refine, right? I don't think that's always true. Like again, I have the minor in writing too, so I know a little bit. But also just like, you know, there's some people will teach that just constantly working is a better way than like waiting for the muse to call, right? So I don't know if we're trying to like physiologically encourage better design. We're just trying to understand the effects it has. Does that? Yeah.
I'm just curious if that
Yeah.
had any truth to it or parallel.
It was also like I mentioned that you talk about anger being. I didn't know if you had read it was more open for creativity than other emotions. Because my personal experience, I find any emotion is great for creativity.
Yeah.
So I didn't know if you had read that anger was more potent or if it was just saying.
If I remember correctly, some of it does say that like anger and upsetness is prominent. But again, the research that I believe the most is that it's short-lived. Right? But yeah, I should have said creativity when I said design because I was thinking about design. But yeah.
Have you looked at design thinking theory?
Yeah, yeah, that informs a lot of what we do. It's the design thinking stuff is. There's a couple of topics that come up a lot, like design thinking, sprint, agile.
It's all based on
Yeah, this human-centered and empathic design are very, very related. Yeah.
and,
Yeah.
you look at psychology books like Design of Everyday Things.
Uh-huh. Yeah. I don't think I have that one on my shelf, but yeah, I do. Yeah.
That's a great book.
Mhm.
Because it looks at design.
There's one too. I'm gonna forget it now. It's blue. It comes from the California School. It's an industrial design book, but basically the left side. Well, let me say every single page is a different design method, which is really cool. Some are better than others. They're all very simple strategies. Like if you've seen House of Quality or QFD, sometimes they call it things like this. There's one page dedicated to it. The next page would be functional modeling. The next page is morph matrices, if you've ever heard any of this. But if I was to, when I get the opportunity to teach a design course, again, I'm trying to be faculty soon, right? That would be a book I would consider instead of a textbook, instead of a design textbook. But yeah, man, I wish I remembered what it was. If I remember, I'll.
And then the other book that comes to mind when people are talking about the different moods and stuff is Wisdom of Psychopaths.
I do not know that.
So it looks at a lot of research studies of psychopaths
Mm-hmm.
and physiologically, psychologically, and how their way of thinking lends itself to creativity in just a different perspective than we would normally think creativity is. So I'm
Right.
interested in that kind of creativity and this anger and that kind of far spectrum of wisdom of psychopaths is very interesting. And has a lot of it's actual data and research.
Sure.
Neurological researchers and neurologists, designers and things.
Yeah, I'll check it out. Yeah.
One last question. With regards to the fact that they missed the link connector, pin driver, the students when they were disassembling, they were doing assembling the disassembly and they were you said they missed the link connector.
For the clothes dryer. Yeah. But that wasn't for the product teardown. That was for the functional. Well, again, I don't know yet because we're still analyzing the teardown one. But
So this is something that's pretty common thing in the industry.
yeah.
Did you see in other products that I think the toilet and they were and then
So not on the toilet or the mixer. I'll tell you something. I'll tell you a couple funny ones. I actually have a file of funny mental models that students give me. There is a graduate mechanical engineering student who put the air going the wrong way in the hairdryer, which is a little concerning, but also like we are aware that the hairdryer is kind of a gendered product, and so we're careful about that. That's why we have the other ones too. Like, huh? Cultural, yeah. No, that's a great point. It's a great point. So I'm not going to sit here and tell you the demographics of the student because that's like what I'm not supposed to do. Funny to see a graduate student not know how this thing works. Another funny one is we do the vacuum cleaners for this, and again, I've scored hundreds and hundreds of these, and it gets funnier every time. It may not be funny the first time I tell you, but like an overwhelming majority of participants label dirt. And it's extremely amusing to see this 100 times. You know, not debris collector or what screen or anything. It's dirtbag. So yeah, that's one of the reasons I love that research so much is like every single time there's a couple of students who do something really wild. Just has either a fundamental misunderstanding about how it works or they label something that I would have never, anyway, no, I don't know what kind of answers. Things that students leave off putting 2 motors in a vacuum cleaner, depending on at least the way I show them, and for the hair dryer. Yeah. I mean, for the clothes dryers, it's funny, like an overwhelming amount of people are very adamant about very detailed listing out the controls. But then like internally, they'll like put a plug and 1 motor and they call it a day. It's kind of funny. And these are mechanical students, not like computer. Yeah. Yep. So.
Let's thank Dr. Murphy one more time.
Thank you. Thanks.
I appreciate it. Thank you all for coming.
Yeah, thanks for being here.